And we have the next paper for the session, getting set up, which is about hints-based geolocation leveraging multiple measurement frameworks. And this is presented by Oliver Gasser, who is a PhD student at Technical University of Munich. His primary research interests are internet-wide measurements to analyze network security paired with infrastructural internet measurements. And we have Patrick, who is a master's student at the same university in Professor Georg Carle's group, and his main focus is on IP address geolocation. So, please.
Thank you very much for the introduction. So, welcome everybody also from our side. This is a joint work together with Quirin Sattler and Georg Carle. And in this presentation, we're going to present our work on geolocating IP addresses. So if people talk about geolocating IP addresses, different parties have a different focus, right? So businesses, for example, are interested in kind of the human-centric geolocation aspect. So if you think about, okay, Netflix wants to know where person A is connecting to the internet so that it can kind of geo-block the content that is being made available to users. Whereas as researchers, we are also interested in the kind of structural mapping and the structural location of the internet when we are talking about internet routers. There are two main approaches if you're doing IP geolocation, and these are either using commercial databases such as GeoLite database or IP2Location database, or a measurement-based approach where you leverage latency to determine a certain location. And in our approach, or our goals, are to combine both of these kind of approaches and take the ease of use of the database approach and combine it with the accuracy of the measurement-based approach. And specifically, we want to focus on internet routers, so the structural mapping part of the internet, specifically because we found that for routers, the commercial databases have a very low accuracy. So before we talk about what we did, let's see what other people already did in this field. So there is a very large body of work which tried to use certain characteristics such as latency, TTL, and so on to do geolocation. However, there is a very high barrier of entry, so you need to do some complex setup for the system, and you need to have a calibration phase and so on. So this is for the measurement-based related work. So DNS-based, there is actually an RFC which specifies how you can store latitude and longitude in the DNS, but it's rarely used. There was another previous work called the drop paper, which obtained good results for certain ground truth domains, but it's not a ready-to-use solution. What we want to provide you here with is a solution that everybody can use. Regarding the database-based approaches or related work, it has shown that the accuracy is kind of questionable for geolocation. So we present to you HLOC, which is the name of our system, and we do geolocation based on hints that we find in domain names. We validate then these hints using latency measurements, and we do this in a multi-step process. So we first do high bandwidth scans from only a few vantage points, and then in the second level conduct globally distributed scans using RIPE Atlas, as also other papers presented here. We obtain an accuracy of about dozens to hundreds of kilometers, so it's kind of a country-level geolocation, and it's ready to use. So we provide the code and everything to you so that you can use it. So let's look at the approach in a little bit more detail. So we obtain various types of codes, so either airport codes, IATA, ICO, and FAA, low code, so this is kind of the United Nations specific format, and also geonames, and we parse those codes. We then obtain reverse DNS data and preprocess certain domains, so to eliminate unusable domains, and we kind of search these the codes that we found here in domains that we obtained from the reverse DNS router dataset. We use some kind of blacklist. I will come to that later in order to remove unusable entries. Once we found these codes in the domain names, we leverage latency measurements to determine whether the hints in these domain names were correct or not. And for this, we have a modular system where we use ZMap, Write Atlas, and in the future we'll also integrate Probe API to conduct these measurements. And using these frameworks, we then validate whether the hints were correct. So what are the challenges when implementing such a systems? So first of all, the search for the location in the domain names should be kind of fast. We wanted to reduce the number of unlikely matches. As you will later see, there are some matches which are just to a very high probability not locations in domain names. And we also wanted to tailor our measurements to the limits that are set by the measurement frameworks. And to do that, we have come up with 3 ideas. So the first one is using a try data structure. And here we apply blacklisting, and to tailor, we use multiple measurement frameworks. And I will go into these 3 now in detail. So a try is basically a prefix tree. And in this prefix tree, we store the location codes. So here you see the example for Dublin. So for each of these entries, there is a location associated with it. And you can see that the lookup is then, as a result, very fast. If we did a comparison, so the initial design of us was using regular expressions, and it was basically unusable. But once we switched to the try data structure, it was very feasible. So to reduce unlikely matches, we use a blacklisting approach. Because certain words in the domains do definitely not hint at a location, and we will see an example here. So this is a reverse domain name, and of course we see a location here which hints at Amsterdam, but there are also, due to the high number of location codes that we collect, FACE is a location obtained in the ICAO dataset. But since it's part of Facebook, it's definitely not a location. So we look for words which are definitely not locations and put them into our blacklist. And this is kind of an iterative process. So we look at the hints or the codes which match the most, and we determine whether it's a location or not. And if it is not, then we put it in the blacklist. Additionally, we also publish this blacklist so it can be used by others, and also even crowdsourced so that everybody can contribute to this blacklist. The next part is to use multiple measurement frameworks. So there are some limitations in frameworks. For example, the number of parallel measurements that you can run, or the requests per seconds that you can perform. So we first conduct measurements with ZMap, which are high bandwidth measurements, to pinpoint kind of the hemisphere of the location. And then we conduct high accuracy measurements from a near location, from a probe near the suspected locations using Write Atlas. So how does the validation concept look like? So we pick up a possible location match from the right to the left label, and then we pick a probe which is kind of close to this location. And then we have a kind of a threshold to validate this location. So an A in this case is the maximum buffer time, because we suspect that the packet is kind of in buffers when traversing routers. And this is the speed of light in fiber optics. So if this validation threshold is fulfilled, we stop. Otherwise, we conduct additional measurements from other probes. So in that case, our maximum error margin is 2,900 kilometers, and that is determined by X and A. Of course, if you conduct your own measurements, you can configure A and X to your liking, and then thus restrict the error margin as you want. So let's look at a concrete example. So we go from right to left. So the first label that we find is New York City. The next one would be a town in Norway. We select the probe near a suspected location, and then we measure the round-trip time from a probe in New York to this IP address. And from that, we get a round-trip time of a little bit more than 1 millisecond. And then from that, you can kind of draw the circle around this the probe location and eliminate the impossible locations, meaning it's not possible from New York City to reach Norway within 1.3 milliseconds. And this is, of course, due to the speed of light limitations. And then we validate the RTT measurement using the threshold that we defined before. And if we input all the variables, then okay, we have a confirmed location. So that was it from my side, and Patrick will now go over the large-scale measurements.
Yes, so we evaluated our approach with IPv4 and IPv6 router domains, and here you see our general results. We also evaluated the difference between domains with IP encoded and without IP encoded, and you can see that in our paper. But now let's look at these results. So we found a lot of hints which are falsified, so we can say these domains don't have a location hint we found, so no location hint was possible. And we could verify 50,000 domains locations. Next we see a map, which some of us may already have seen in the PhD school. So these are the locations of the RIPE Atlas probes which are available a few days ago. And we see that it concentrates on Europe and the US, and the rest of the world is not as well covered. And now these are our validated domain locations. They look similar to the RIPE Atlas locations of the round-trip time measurements. So we compared us against the drop approach, and for that we had to reproduce the drop hint generator using their rules, and we evaluated them against their ground truth domains. And now some interesting findings. For the Kogan domain, we found that we could validate a fourth of all domain location hints, but we could also falsify 7% of all location hints found by drop rules in this domain. So you infer, in 7% of all cases, you infer the wrong location based on our round-trip time measurements. For NTT, we have another interesting case. Drop claims that 96% of all domains contain a location hint, and they are 100% precise about the location, comparing against the ground truth they got for the provider. But our production only reached 45% of location hints in domain names, and we investigated that further, and we found that NTT uses custom CLI codes. CLI codes are normally only used in the US, but they also use it for the rest of the world. So, and these are not non-public codes, and we don't have them, so we cannot find these location hints because they are not public, but Drop seems to. And now an example where we find a location in a domain name, but Drop isn't able to do because they have a simpler pattern matching. So this is a more complicated domain name where there is the hint for Frankfurt in it, and we could validate it, but Drop found a location hint. So now, how well do location databases work? We compared against maximum Scarolite and the P2 location, and we see that we could that a lot of locations are wrong in the databases. 44% for Geolite, a bit less for the IP location, only 12%, but still that's a huge number if you try to infer topology. For drop, we also evaluated it against all domains, and for over 80%, they didn't even generated a location hint. So that's not as useful. So now summarizing the results, we find more location hints which we can then test, and commercial databases aren't usable for router geolocation because they're really bad in it. And IP encoded domains also contain less locations, so they are yet less usable. That was also fine. So what we are going to do next is we want to prove our probe selection, because Web Atlas provides, for example, the first and second hop latency, so we can pick better probes with less latency. And Web Atlas also plans to integrate geolocation functionality, and they contacted us about that. We want to make a web service where it is possible to geolocate hosts, and like Oliver said before, we want also to integrate more frameworks like Probe API. Now Oliver.
Okay, yeah. So here you can see our key contributions again. We make all the data and all the code and all the blacklist available on our site. It's also on an archival library server at our university, so it should stay there for some time and not be offline soon. Yeah, thanks for your attention, and we'll be happy to take questions.
Yes.
Yes.
I wonder, did you find any ripe Atlas probes that weren't where they claimed to be?
So that's a good question. I think that's something which we will look into in the future, where we are planning to select multiple probes. Mm-hmm. So if we're selecting 3 or more probes, then the likelihood of 3 probes being in the wrong location is reduced drastically.
So I had 2 questions. The first one is that is there any reason that you're not doing triangulation for pinpointing the exact location of that interface? So when you're doing a single RTT probe, there's a chance that you might be sitting in midway between those 2 locations, and you cannot dismiss any of them. But if you're doing triangulation, you will probably end up with a better accuracy. And the second question is that you guys also compare your results with Pathlogit. I don't know if you're familiar with it or not. It's a tool, basically the same tool developed by Paul and Arthur group.
So the last question, I'm not familiar with that tool, but I think we could definitely look into that. Regarding the first question, so I think that also kind of goes in the, we want to improve our probe selection process. And in that process, if we select multiple probes, we would select them such that triangulation is usable then. Yeah.
I have a question. So in your data set, how many names or IP addresses do you have? Because you compare to like Geolite, but you have a very large coverage. You can ask for any IP addresses.
Mm-hmm.
So like, how many entries do you have in your database?
We tried to, so we focused on routers, right?
Yeah.
So we use the CADA router DNS name dataset, and this is the number of entries that are in these datasets, and here you can see how many already are removed where we do not have a match, and which are then removed after we get a timeout value.
And for infrastructure, like if you ping like Google, like that's something we tried recently. Like looking at, like you try to do a trace route to Google DNS, when you are getting close to the DNS and you're in the infrastructure, there is no name, there is no DNS name for routers that are within the infrastructure.
Mhm.
I was wondering, like, can you, using the location of routers before, could you try to infer it where are those routers within Google?
So that would think a very good idea of combining the knowledge that we have of the routers before on the path, and then kind of determining, okay, from that there is a latency of plus X, and then kind of having another radius, okay, it's within this margin of error. So I think there are possibilities of how to kind of gather more location hints. So we mostly focused on the DNS parts, but I think there are valid, other valid sources that could be used and that are easily extendable. Yes?
So one thing that we have at the SEC is OpenIP map, which I'm pretty sure you're aware of by this point. I'm pretty sure we're talking to you about it.
Yeah.
But OpenIP map, for the broader audience, has the overarching goal of providing better geolocation data for fixed infrastructure such as this. And this sort of stuff is precisely the sort of technique that we want to incorporate into our work. So this is great.
Yeah, thank you. Yeah.
We have more questions? Or I can ask a few. So we saw a lot of Anglo-Saxon names. We had Amsterdam, New York, Norway, and so on. And of course, we saw that the probes are not available in Russia and China and so on. But do you have some idea if they are using the same naming structure? I mean, including geolocation names, also in that part of the world.
So since we cannot validate, or since there are no probes deployed there, it's difficult to know whether the codes that we find there are actually valid or not.
Just not if you saw some trace route going through Russia, going through China, and I mean spontaneously, okay, so this is Shanghai or Beijing or Moscow or some such. I mean, if the operators there are using this kind of naming scheme.
We didn't do specific trace routes to China, no.
So I also have another question. I mean, these names are made up by the operators. Did you contact operators to ask them of their naming scheme? I mean, since at least the Tier 1 operators, I mean, they must have some good structure for this naming on different locations. And I mean, if you ask them, you would probably get a good specification. Or maybe it's kept secret, I don't know. But did you talk to some operators?
So we talked to some people that are in a project with us, but we didn't contact Tier 1 operators. Yeah.
So did you get their naming plan?
They didn't give us their So we thought, okay, if even not the people in our project give us their naming plan, there is no. Yeah.
Okay, if there are no further questions, let's thank the speakers again.